In this session, let us discuss about interpole and compensating windings of DC machine. Basically, with waveforms and all we can discuss, okay? But it is concise course, and we don't have much time, okay? So in the simplest way possible, we have to tackle the gate, okay? That's why in the simplest way possible I'm going. Now, for example, this is N pole, this is S pole, G and A, geometrical neutral axis, and this is generator. So under no load conditions, flux will flow in this direction. Okay, at no load conditions, such that if flux is flowing in this direction, 90 degrees to this flux is going to be this M and A, magnetic neutral axis, will lie upon G and A only, geometrical neutral axis, such that what will happen means there are no currents, armature currents, so armature flux will not be there. So for example, once it is loaded, okay, so once it is loaded, let me think of, first of all, this generator is being rotated in this direction, because for a generator rotation is input. So first of all we have to start rotating the generator, then only voltages will be induced. Now let us think of voltages. For example, means flux is flowing in this direction and conductors are moving in this direction, so this is going to be cross right hand, okay? So this is going to be cross voltage, cross voltage, cross voltage, cross voltage, cross, and dot voltages. Now the moment you connect some load here, what will happen? For example, brushes are here only. Okay, so in our practical case also, brushes will not be changed here. Okay, because magnitude of armature current will be decided by whom? Load. Okay, if load current is more, under that condition armature current is more, in the sense armature flux will be more, so interaction of field flux and armature flux will be more, and repositioning of M and A will be more, or that particular angle of from G and A to M and A angle will be more. For example, if my machine is lightly loaded in the sense my current is not full load. Okay, so when the moment my machine current is not full load, means less current, armature current will be less, armature flux will be less, so interaction will be less, so M and A shift from G and A is going to be less. So we cannot automate this. Okay, so my brushes will be always placed here only. Okay, now if brushes are placed here, generator voltage and current direction should be same. So these is going to be dot, these are currents here, and these are crosses. These are crosses. Okay, now what is happening here? Already we know from the analysis of armature reaction of our previous sessions, we know that in generator, at leading pole tips flux will be weakened, at trailing pole tips flux will be strengthened. So what is happening here? If I am rotating the rotor in this direction, so this pole I am about to capture, this is going to be leading pole tip, so leading pole tip flux should be reduced. And here if I move like this, I have to leave this aside and I have to go in this direction, so this is going to be trailing pole tip flux density will be increased. Now here also, if I am rotating here, this flux, pole tip is leading me. If I am rotating like this, flux tip, here pole tip is leading me, so this is going to be leading pole tip. Here flux should be reduced, and here flux density should be increased. Okay, such that what will happen? My resultant M and A, okay, our resultant flux will be in this direction, such that my flux will take a turn from here and it will go here and it will go like this. Okay, so M and A got shifted. For example, here this is going to be M and A because of load current. Okay, so what does it mean? For example, if my flux is flowing like this, so in this direction, okay, so because of armature reaction, flux is flowing in this direction, means that what is happening here, from here to here, it became N pole, S pole, this is S, no, so it became S pole, and from here to here it became N pole. Okay, now if brushes are at G and A, means is it a problem or not? Yes. Okay, because brushes are here only. Now, because of this particular M and A shape, brushes are not positioned at M and A, means that induced voltage or voltage tapped across the brushes in generator will be reduced. Okay, so that is one thing. And second thing is because of commutation, some sparking and all those will come. So ultimately what I am about to do is, if I can keep a small, for example, this particular at no load conditions, M and A and G and A will be aligned. At loaded conditions, M and A is getting shifted. This particular angle of M and A shift will be decided by armature currents. Now, for example, if I can keep a small pole here, if I can keep a small pole here, if I can keep a small pole here, interpole, okay, and if this particular, for example, for this, I'm going to have currents, conductors, okay, then for example, if it is producing some flux such that if this S pole up to here, no, if this S pole can be reduced to 0, means that it should be N pole. Okay, so if it is N pole for a generator, for example, N pole, then what will happen? It is under a S pole region, and this N pole, such that whatever is the S pole flux density or flux here, if it can be exactly compensated by interpole, then like my M and A will come back to G and A. Getting my point, right? So for example, see here, focus here, all of you here. So point here is, means at GN, because of MNA shift, what is happening? This particular GNA is in the region of S. For example, if I can keep N pole here, a small pole, okay, N pole here, then S pole region plus N pole, then what will happen? It will be like, come back to 0, such that this MNA will come back to GNA. Forcibly we are going to do it. Now point here is, this MNA shift will be decided by load currents, okay, and my armature conductors are in rotor, interpoles are in stator. So for example, if I can connect this in series with the armature currents, for example, if currents flowing is IA, armature currents, it is not conductor current, because conductor currents will be there inside the armature, means after the brush what will be there? After the brush, armature current or load current will be there. Now if I can design this interpole in such a way that means because of armature conductors currents, means the pole strength of this S pole will be decided at GNA. Now if the same armature current flow here, if I can design these particular number of turns per pole on the interpole, then what will happen? Because of the armature current, shift is happening. Because of this armature current, this compensation is happening, such that this particular N pole can exactly compensate it, such that this shifted GNA, MNA will come back to GNA. So means my interpole should be connected in series with the armature currents, because means my this particular shift is happening because of load currents inside the conductor armature. Okay, so this also, if it can be of armature currents only, then compensation will be exactly proper. Okay, and one more interpole, like interpole has to compensate armature MMF at GNA. One thing, and second thing is, of course, without commutation, I may not be able to tell you properly about this, but that's fine. Okay, so see here, for example, let us think of conductors. Okay, so if you are sitting on this conductor, okay, so once you sit on this conductor, how much is the current? For example, here current is IA, armature current. This conductor current is going to IA by A, conductor current to IA by 2, because 2 parallel paths are there, for example. So this is going to be IA by A, cross IA by A, and it is getting rotated in this direction by generator. So you are sitting on this conductor, cross IA by A, cross IA by A, cross IA by A, cross IA by A to dot IA by A. So means only, I discussed in our previous sessions also, in armature inductance need not be considered in DC machine, because my conductor current is trapezoidal. Okay, so conductor current here, for example, this is 5 ampere, just like that, 5, same current. So there will be no change in current. So inductance need not be considered. Now plus 5 to minus 5, minus 5, minus 5, minus 5, minus 5, minus 5 to plus 5, means that except in the commutating zone, we need not bother about inductance. Okay, now anyway, forget about except commutating zone, let us think of commutating zone. Okay, in the sense wherever you are keeping the brushes at GNA, then what will happen at the GNA, at brush axis, at brush, my current should be changed. Okay, so the current is getting changed from plus IC to minus IC. For example, my conductor currents, if you get any doubt here, go through waveforms of induced voltage, currents, MMF and all. We have done one video, just go there. So my conductor current is going to be IA by A, plus 5, plus 5, plus 5 to minus 5, minus 5, minus 5, minus 5. Okay, so this is going to be commutating time, tau c. We have problems on commutating time and all, we are going to discuss. Okay, so point here is very simple. From here to here inductance will not be there, from here to here inductance will be there, from here to here inductance will not be there. So in the commutating time, because of inductance, L di by dt, because di by dt is existing, so L di by dt will exist. So because of inductance, some reactance voltage will be induced or not? Yes. Okay, so that reactance voltage, because of that reactance voltage, current reversals will become difficult. That is called as commutation, like linear commutation, delayed commutation. Some commutations will be there, I know, but you need not know for gate, because time is less. Okay, so anyway, because of that current reversals, some reactance voltage will be induced. Now, because of this flux, for example, my interpole is having two functionalities. What are those? First of all, my armature MMF across this should be compensated, and my interpole has to provide some more flux. Okay, because for example, this is the flux. If conductor is getting rotated, so because of this flux, in this induced voltage will be there. Now normally, in a conductor, when current reversals happen, induced voltage will be there. Now if this particular conductor induced voltage, because of current reversals, because of inductive reactance, if it can be compensated by flux, current reversals will become smooth and commutation will become smooth. That is my point, right? So point here is interpole is having two functionalities now. One is to compensate armature MMF, and second thing is in order to provide some extra flux, such that because of that extra flux, rotational induced voltage in the conductor should be exactly compensating the reactance voltage induced because of inductance current reversals. Okay, so interpole is over. Okay, what is the conclusion here? This particular interpole polarity should be in the generator. This is GNA, this is N, this is N. So my interpole polarity, this is actually very important conclusion here. So interpole, because some questions are there, we are going to solve anyway. Interpole polarity should be the polarity of the main pole ahead in case of generator, or main pole behind in case of motor. Because if generator is getting rotated in this direction, motor direction of rotation will be reversed already. Okay, so point here is very simple. My polarity of the interpole. Okay, so is it N pole or S pole will be decided by the main pole ahead in generator. Keep that point in mind. Okay, now let us think of how many number of turns should be placed on each interpole. Okay, so what is armature MMF? We need not remember anything. Okay, armature MMF, ampere turns. So ampere, conductor current ampere into number of conductors by 2 turns into per pole. Okay, so this armature MMF should be compensated by interpole. Okay, plus some extra flux it has to provide. Now for example, that extra flux that has to be provided is B. They will give you flux density. Okay, so what is B? Just a minute. What is B normally by our equations? Mu naught, mu r, h. Okay, mu naught, mu r, h. So this is going to be mu naught, mu r, Ni by Lc, h. Okay, so magnetic field intensity, transformer, go back. Okay, so for example, what is MMF required to compensate air gap? Because between interpole, actually one thing I may have to tell you here, the air gap length here will be very less, air gap length here will be more between my armature and the interpole, because of some reasons, forget about it. Okay, relative permeability is going to be 1. Under that conditions, what is the MMF is going to be flux density into length of air gap, flux density into length of air gap divided by mu naught. Okay, will give you MMF required. So my interpole, what it has to do, my interpole MMF should be armature MMF, should be compensated, plus flux density into length of air gap divided by mu naught. Okay, why length of air gap is only considered? Why not for example, interpole N will come here, S will come here, N to S it will go, and again it has to travel, no? But we are going to consider relative permeability of magnetic material as infinite, and we are going to consider only length of air gap. It's a big thing, we will discuss later. Okay, so this is going to be the formula. Now, how much will be the number of turns on interpole is nothing but F of interpole, ampere turns of interpole divided by number of turns are required. So current. What is that current which is flowing in interpole? Armature current. Problem solved. Okay. Now let us think of compensating winding. Okay, so if I think of compensating winding, okay, basically, like, for example, under normal no load conditions, let us think of this as the pole. Okay, so my flux density, if you see, my flux density is going to be flat top like this. Okay, now if you apply load, what will happen if, for example, generator direction of rotation is in this direction, so this is going to be leading pole tip, this is going to be trailing pole tip, so here flux density should be reduced and here flux density should be increased. Okay, so here flux density should be, don't focus on these things, okay, not required. So here at this pole tip flux density has to be reduced, at this pole tip flux density will be increased under loaded condition. Now let us think of, like, one beautiful example, that is welding generator. Okay, so in welding, what will happen in welding? My load variations are going to be tremendously high. For example, black, no load, red, load, black, no load, red, load. For example, in welding, what will happen? For example, these are the two electrodes which I want to weld. Okay, so what I have to maintain? I have to maintain some air gap such that it will be melted and it will welding. Okay, but who will maintain a small air gap? Nobody will maintain. He will short circuit. Again, he will open circuit. Again, he will start welding full load, short circuit, open circuit, full load, short circuit, open circuit. So load variations are going to be tremendous. Under that condition, what will happen? Flux density at no load, full load, no load, full load, no load, full load. So because of this variation of flux density, we are going to get induced voltages, statically induced voltages. For example, here one conductor is there. Okay, so on the armature, here one conductor is there. Okay, so upon the conductor, induced voltage will be there or not? Flux density. Getting my point, right? So at no load, like, black, flat top. At load, red. At no load, flat top. So when load variations are high, flux density variations are high, induced voltage will be there. Okay, already our DC machine is not much useful machine. Okay, basically because of these flux variations, because of that statically induced voltage, stress upon the insulation of this is going to be high. So we may have to compensate. Normally all DC machines will have interpole winding. But when load variations are tremendously high, we may have to think of compensating winding also. Okay, what is meant by compensating winding? For example, if I can keep, red. Okay, so in pole shoes, if I can keep some conductors in pole shoes, such that under the pole shoe, like, if it can be compensated, this particular flux variation or flux density variation, if it can be compensated, then what will happen? Means at no load also it will be like this only, at load also it will be like this only. Because at load, what is happening? It is trying to go like this. But this particular compensating winding, it will provide some flux to make it straight. Okay, so that is the concept of compensating winding. Okay, so for example, let us come back to here. Okay, so in this, what's happening here? Forget about interpole now. Let us think of compensating winding. All machines will not have compensating winding. Okay, so high capacity machines, and when load variations are tremendously high, then only, like, you are going to get compensating winding. For example, here on this, let me keep off. All colors are over. Okay, let me keep off blue here. If I can keep some compensating turns for two poles, compensating conductors for single pole. Okay, now we know that, like, for example, if you think of only cross mag, forget about this. Okay, if you think of, like, cross magnetizing amp, because of that cross magnetizing only, like, load variation, because of that cross magnetizing ampere turns only, this variation is coming. So in order to, like, compensate that, in order to compensate cross magnetizing, for example, this is going to be cross, this is going to be dot. Armature conductors red, armature conductors cross. So I should provide these in such a way that it should be like this. Okay, so for example, let me explain. For example, if it is like this, so means that it is going to be cross, it is going to be dot. Okay, so under that condition, what will happen? For example, armature is not loaded. Okay, so armature is not loaded in the sense my after brush only. This is stator, no, pole shoe is stator, interpole is stator. So armature is not loaded. Not loaded. Under that conditions, what will happen? Armature flux will not be there. Current will not flow through these also. Current will not flow through these also. But for example, if armature is loaded, then means this particular what do you say, M&A will try to shift, but it will come back to its original position because of this. Okay, so my interpole is compensating across GNA, but what about here? Flux variations are going to happen like this. Okay, so in order to remove this, if I can have, for example, because of the load currents, armature MMF is this, compensating winding MMF is this, cross here dot here, compensating winding MMF is this. So means the moment load is connected, the moment compensating winding will come, such that both will be compensated. Getting my point, right? So compensating winding will try to compensate the cross magnetizing effect under the pole shoe, such that these variations will not happen. It will come back to its normal position. Okay, so one thing we have to understand here, what is that? Per pole, conductors will be there or turns will be there, conductors will be there. For two poles, turns will be there, compensating winding. For example, here there is a concept of pole arc by pole shoe. Because under the pole shoe only we are going to compensate with compensating winding. So, for example, now if I have both interpole and compensating winding, if at all, if I have both, okay, if I have only interpole, already we have done, we got the formula. Now if I have both interpole winding and compensating winding, how to do? Okay, we are going to calculate FAR, armature MMF, ampere, turns per pole. Okay, in that pole arc by pole shoe, pole shoe is this much, pole arc is this much, pole pitch. Okay, so out of total pole pitch, how much percentage of pole shoe is covered? In that, armature MMF has to be compensated by compensating winding. So for example, let me think of pole arc by pole pitch. Pole pitch is 180 degrees. Out of that, how much pole arc is covered? About this already we released the video. It should be more or less recently. Now pole arc by pole pitch is alpha, for example, alpha or beta, whatever it may be. Okay, so out of all armature MMF, 1 minus alpha of armature MMF should be compensated by compensating winding. Okay, so pole arc by pole pitch. Okay, so I'm sorry dear, I'm sorry, I did a small mistake. Now, pole arc by pole pitch area should be covered by compensating winding. So, alpha into FAR. Okay, out of total armature MMF, if pole arc by pole pitch ratio is 75%, out of total 100%, 75% is covered by pole shoe. So, that 75% of FAR should be covered by compensating winding. Now, actually, many guys have a doubt, how to calculate number of conductors per pole. For example, means MMF. Armature, ampere turns is MMF. What is ampere? IA or IA by A? IA. Because after the brush, my compensating winding is in stator. Okay, so IA, current, into number of turns of compensating winding. Okay, so what is number of turns? FCW by IA. So Z, compensating winding, because conductors only will be there per pole. Okay, not turns, conductors only will be there. Z of compensating winding, conductors, is going to be FCW MMF by IA, turns into 2 is going to be compensating conductors per pole. Done, deal done. We did not remember anything, we need not. Okay, this fine. Polar by pole pitch, fine. Okay, now what about remaining portion? Remaining portion has to be compensated by interpole winding. So for example, means MMF of interpole winding should be alpha of FAR is covered here. 1 minus alpha of FAR should be covered by this plus means interpole. Where will be the interpole? Upon the GNA, upon the brush axis. Getting my point, right? So the moment brush axis is there, at the brush axis, because of current reversals, some voltage will be induced, statically induced voltage, reactance voltage, that has to be compensated by rotational voltage. So we have seen here B into LAG by mu naught. So plus B into LAG by mu naught. Okay, so in this way, compensating interpole winding MMF has to be found. For example, they will ask you number of turns on interpole is going to be MMF of interpole divided by IA or IA by A. IA, because interpole will be in stator. After the brush it will be IA, before the brush it will be IA by A for generator. Okay.